Okay, so I've set this up. I didn't have this before. So deleting. Okay. The length of the wire was actually something that we measured during the experiment, and this is in meters. This is going to be important later. So, first thing we need to do is deduce the mathematical relationship between force and current, including the uncertainty of the slope. So this is something that you did in your IA1. So the relationship between force and current is that current is our independent variable on our x-axis, and our force is our dependent variable, in that the force depends on the current, right? And we can see this clearly in this relationship. As we increase our current by a set increment, the force depends on that value as we see an increase, okay? So what we are going to do is take our mathematical relationship that's given, and okay, we can have a look at this in terms of what it represents. So y is equal to 2.47 times 10 to the negative 3. I'll say 48 just to keep it a bit more simple. I'm just going to say times 10 to the negative just to keep that a little bit more clear also. Times 10 to the power of negative 5. Okay, so we have our linear relationship here, and this is given by a y is equal to mx plus c sort of thing here. So if we write our y equals mx plus c, this is our usual linear format. You can see our m. I'm not going to hold that. Okay, our m is our 2.48 times 10 to the negative 3. Our x is x, and our y, our c is negative 7.09 times 10 to the negative 5. Okay, and what we can do is relate that to, well, what are our x and our y? Our x is current, and our y is average force. So I'm going to rewrite this as F for force is equal to the gradient value multiplied by current minus our y-intercept. Okay, that is meant to represent current there, that I. It's sort of hard to tell. Yeah. So we can start to think about what formulas we have relating to this, and I'm just going to pull one because directly from the formula sheet. So we're looking at the force on a current carrying conductor in a magnetic field, and we have the formula F is equal to magnetic field strength multiplied by current multiplied by the length of the current carrying conductor in the magnetic field multiplied by sine of theta, which is, where is the, yeah, okay. Now, in this instance, our theta, our angle that the wire is being affected in the magnetic field, the theta is 90 degrees, okay? So that's just going to be equal to 1. That means if we were to relate our formula to the equation of the line, we could say that our gradient, I'm going to rewrite this and say that it's actually force is equal to magnetic field strength multiplied by length multiplied by sine of theta, and then that's multiplied by I. Well, this here looks like the gradient. Okay. And in this instance, that is equal to 2.48 times 10 to the negative 3. So now we can say that, am I jumping ahead? Maybe a little bit. Okay. We'll leave it there because down here we determine a value for the magnetic field strength. I was about to jump ahead and do that. So what I'm going to do now is go and determine the gradient uncertainty, and that will be like the range of uncertainty. It's going to be my maximum minus my minimum divided by 2. And the same goes for my y-intercept. So this, let's just determine those values. I'm going to bring this down here so we can have a look. So the uncertainty in my gradient in this value here, from our linear relationship of the trend line that fits through our data points, the uncertainty in that gradient is equal to max gradient minus min gradient divided by 2. It's like our range over 2, right? Our max value minus our min value. So our max is going to be equal to, I'm just going to change these quickly. Format, trend line label. It's not working. Sorry, I just wanted to increase the number of sig figs in that, and this is my maximum trend line. Just because I saw that if we were to minus some of these values, we probably wouldn't get much difference, or a clear enough difference. Okay, so just going back here, my maximum gradient is going to be equal to 0.002850. My minimum gradient, is going to be equal to 0.00201. And therefore my uncertainty is just equal to my max minus min divided by 2. So we can continue on, do the y-intercept, which is similarly as here. It's the max y-int minus the minimum y-intercept divided by 2. So max y min y. The maximum y-intercept is equal to negative 0.00266, and the min is equal to 0.00018. I wrote this down incorrectly. Yeah, okay. Now, we are looking for the range between these values. So if you consider this to be a number line, negative 0.00026 is over here, and positive 0.00018 is over here. We need to make sure we are getting that difference. So just for the sake of this, I am going to, because our uncertainty will be plus or minus, I'm actually just going to say our uncertainty is equal to actually no, that won't matter. A max minus a min divided by 2. Yep, all good. Okay, now we can write the full equation. So our force, I'm sorry that this is all in scientific notation, it's pretty ugly, but this is the best I've got on Excel. Maybe I'll take this away and just go plus minus, and it's our gradient, uncertainty 0.00042 I, and we'll go now we have our y-intercept is going to be that plus or minus 0.000223. Okay, now it is a negative value here, but even if I made this negative, it doesn't make a difference because it would be a minus a negative or add a negative. Either way, same thing. Cool. So we have our full mathematical relationship here. This is including uncertainty. Oh, that is not good. Okay, so we have our gradient plus or minus some uncertainty in the gradient in the units of that gradient, and we have our y-intercept plus or minus some uncertainty. So we can now go on and have a look at the average magnetic field strength, and that's sort of coming back up to what I was doing up here. So we can look at the formula as representing our, if you can see here what's highlighted, BL sine theta. That is actually our gradient value, and that gradient value we can see maybe a bit more clearly here, 0.00248. Okay. For the moment, we are going to disregard the uncertainty value in this, and we'll bring that back in a little bit later when we do the percentage uncertainty. Okay, so the gradient is equal to, let's write that in there, gradient is equal to 0.00248, and that is actually equal to BL sine of theta, but in this instance theta is 90, and therefore sine of 90 is 1, and we will disregard that. So looking at this now, we can say that the magnetic field strength multiplied by the length of the wire within the magnetic field is equal to this gradient value. And therefore the magnetic field strength B is equal to the gradient divided by the length of the wire within the magnetic field, which is all the way back up here, and I'm going to reference that cell, 0.037. Okay. So now we have our answer in Teslas. Okay. So that is how strong the magnetic field was based on our measurements of weight at certain currents. Okay. Now, that value is not perfect because we see here there is uncertainty in our experiment. You can see all the way back up here we have uncertainty within our experiment. In our trial values there is a range, and therefore that propagates all the way throughout the experiment. We can determine how much uncertainty is within the experiment by taking our gradient uncertainty and looking at our uncertainty of our measuring tool for the length of the wire, which was the smallest increment divided by 2. And in this case, a meter ruler, well, like a 30 centimeter ruler was used, and it had 1 millimeter as the smallest increment, and therefore half a millimeter is going to be the uncertainty. The thing here is that we need to note is for our uncertainty values, yep, that's what we're doing, step 3, so we've done step 1 and 2. For our uncertainty values, we have, they are in units, they are in set units. If you think about it, the gradient is equal to the magnetic field strength times the length, so the gradient uncertainty is actually in like Tesla meters, okay? And in the case of our uncertainty of our measurement of the wire, that is in meters, okay? So we can't really just add them together, they're in different units. So what we need to do to propagate uncertainty, we need to convert our uncertainty values into a percentage, and then we can propagate them across and determine an overall percentage uncertainty for our value of magnetic field strength. Okay, so since uncertainties have associated units that do not align, convert them into a percentage, then propagate the uncertainty. Okay, so what that means is we need to convert our gradient uncertainty into a percent. And that is, how big is this uncertainty when we compare it to our gradient value? Okay, so we might say percentage uncertainty of gradient is going to be equal to our uncertainty value, so 0.00042 divided by our gradient value, 0.00248, multiplied by 100. Okay, so 16 or 17% uncertainty. Our percentage uncertainty of the length of wire, or of the wire length, is going to be equal to the smallest measurement, which is 0.0005, divided by the actual measurement, okay, multiplied by 100. And that's only 1%, and generally that's quite small. You can imagine though, if we were measuring something that was 2 millimeters, that percentage would be a lot higher. Okay. So finally, we can propagate this uncertainty, and since we are dividing our values together, we can just add our percentages together. Okay, so the percentage uncertainty for B, our magnetic field strength that we've calculated here, the percentage uncertainty is equal to these 2% added, right? You can imagine one amount of uncertainty wouldn't reduce the amount of another uncertainty. Uncertainty is sort of compounded and they add together. So overall, we have our magnetic field strength is 0.067027 Tesla, plus or minus, I'm just going to have to do this here so it doesn't actually think it's a formula, plus or minus, well, what we could do is turn this percent into Tesla units. So convert it from a percentage back into Teslas. So I'm going to multiply my answer by the percentage uncertainty. Okay, and I will get, just need to convert that into a decimal and out of a percent. So my answer says that my value for magnetic field strength is this, but it could be within some range. Now, it does ask, so determine the uncertainty. Cool, we just did that. Calculate the maximum and minimum magnetic field strengths. Well, the maximum, the largest strength within our uncertainty, magnetic field strength max, is going to be equal to our magnetic field strength plus the uncertainty, and our minimum is going to be our magnetic field strength minus the uncertainty, hence the plus or minus. And looks like we have pretty much finished. Explain why the balance pan moved down when a current passed through the wire. Well, I will let you investigate that. So overall, we have, I guess, a few answers. I might just add, just for clarity, so you'll notice I'm adding the units after, in this case, because I'm going to add the percentage uncertainty. We don't want to in this case, the units Tesla do not apply to the percent. It is some amount of magnetic field strength plus or minus a percent. But since we converted the percentage back into Teslas by multiplying this by this, we can now say it's the magnetic field strength plus or minus some value of Tesla. And then therefore that leads to our. So this is what we have ended up with as our answers. I don't know if that helps. That maybe looks a bit worse. So lots to get through. It is really important that you are able to follow along with this and complete this in preparation for IA2. Okay, bring any questions to me in class, and if you would like for me to go over any of this and the reasons why, let me know. Thank you.